Systems of linear inequalities. Just like a system of equations was a set of two or more equations using the same variables, a system of inequalities is a set of two or more inequalities using the same variables. When we're finding the solution to a system of inequalities, we're always going to do this using a graph, and the procedure is really similar to when we found the solution to a system of equations using a graph. So let's pretend this, instead of being a system of inequalities, we're a system of equations. I would graph both equations on the same grid. I've done that here in Desmos. And then I would look for the point where the two lines intersected. This point, x equals -1.5, y equals 1.5, this intersection point is my solution to the system of equations. When I'm finding the solution to a system of inequalities, I'm not looking for an intersection point. I'm looking for an overlapping region. So I graph both inequalities on the same grid and then look for the place, the region, where the shading of the two inequalities overlaps. Let's do that for this example. For this example, my first inequality is in slope-intercept form. So when I graph the boundary line, I can use the y-intercept of 2 and then the slope of 1/3. So boundary line first, y-intercept on the y-axis of 0, 2, and then rise over run of 1/3. Up 1/3. To go left, instead of going up 1, right 3, I go down 1 and left 3. Down 1 and left 3. My boundary line is going to be dashed because I don't have an equal sign here. That means points on that boundary line are not solutions to that inequality. So boundary line has been graphed. Now I need to determine my shading. Is my shading above or below the line? I can use the inequality symbol since this inequality is in slope-intercept form. And since I have a greater than sign, that means I'm shading the points above the boundary line. So I'm going to go ahead, and shade that region, the area above the boundary line. This is my solution to that first inequality. So my solution to the first inequality is all of these points, this infinite number of points above that boundary line. Now to graph the system, I need to graph the second inequality. The second inequality is in standard form, so I'm going to graph that using intercepts. To find the x-intercept, I set y equal to 0 and make this an equation. The boundary line, I think about it as an equation. 2x equals -6. Solving this one-step equation gives me the x-coordinate of my x-intercept. So my x-intercept is x equals -3, y equals 0. For my y-intercept, I set x equal to 0. So now I have the one-step equation, -2y equals -6. That gives me my y-coordinate of my y-intercept. So my y-intercept is x equals 0, y equals 3. So I'm graphing the boundary line using intercepts, and I need to determine, should I be connecting those intercepts with a dashed or with a solid line? Since there is an equal to part of the symbol, greater than or equal to, I'm going to graph them, connect them with a solid line. Whoa. For my shading, I'm checking to see, does the origin, does 0, 0 lie in the shaded region? So I'm going to plug in 0 for x and 0 for y. That gives me 0 on the left-hand side. Is 0 greater than or equal to -6? Is it? Yes. Yes, it is. 0 is greater than or equal to -6. That tells me that the origin should lie in my shaded region. So since 0, 0 makes this inequality true, that means it's in my solution set, and this side of the boundary line is my solution to the second inequality. So every point in red is my solution to the second inequality. So here's my system. I've graphed y is greater than 1/3 x plus 2, and I've graphed 2x minus 2y is greater than or equal to negative 6. Now this is not my solution. My solution to the system is the overlapping region only. So only this purple region, and it would have nicely turned purple for me if I were doing this using colored pencil or highlighter on my own. This purple region only is my solution to the system. Blue region, solution to the first inequality. Red region, solution to the second inequality. Purple region, that's the region that lies in both blue and red. That is my solution to the system of inequalities. So this is pictured for you below. This is my actual solution to the system. When you're doing this by hand, we don't expect you to sort of erase the non-overlapping region, but we do want you to know it's only this purple part, only this part pictured below, that is the solution to the system of inequalities. Last, we're going to look at this follow-up question. Is -3, 4 a solution to the system of inequalities? We're going to answer that question just like we did a similar question, is an ordered pair a solution to a system of equations? We're going to plug this ordered pair into each inequality and see if it makes both inequalities true. So let's plug x equals -3, y equals 4 into that first inequality. Is 4 greater than 1/3 times -3 plus 2? Is 4 greater than -1 plus 2? Is 4 greater than 1? Is it? Yes. What that tells me is that this ordered pair is a solution to that first inequality. I can see that because the point -3, 4 does lie in the blue region. It is part of the solution set to that first inequality. Is it a solution to the second? Let's plug in -3 for x and 4 for y. Is 2 times -3 minus 2 times 4 greater than or equal to -6? Is -6 minus 8 greater than or equal to -6? Is -14 greater than or equal to -6? Is it? No. No, it's not. And I already knew that because -3, 4 is not in the red region. It's not in the shaded region for that second inequality. What this tells me is that the overall answer to the question is no. The ordered pair -3, 4 is not a solution to the system. I can see that from the graph because this point, -3, 4, is not in that shaded region. It's not in the overlapping region. I may have been tricked if I had just looked at this graph and thought that yes, it was a solution since it was in a shaded region, but it can't just be in one of the shaded regions. It has to be in that overlapping region to be a solution to the system of inequalities.